This is Brian Putt. This is the fourth video in a series that will discuss the value of imperfect information with uncertain demand curves. We're going to do this analysis with Excel, and Monte Carlo, and without decision trees. If you want a copy of the model, please send me an email at brian@theputts.com. In the first part, we talked about this case study storyline, and in the second part, we introduced the Excel model, and in the third part, we talked about the value of perfect information. And I'll kind of pick up where we left off there and then talk about the value of imperfect information. Just briefly, the key issue here is the ticket demand. And we've assessed that there are three different demand scenarios as shown here in these three lines. And in addition to that, there's a 20% uncertainty even when we know which line we're on. In our value of information analysis, we're going to assume that the information tells us which of these three demand lines we're on, but nothing about the 20% uncertainty. So the conceptual decision tree is that if we conduct the survey, we get some results, we then can make a decision whether to conduct the play or not, and the ticket price that we would set based on the results of that survey. We then have the 20% uncertainty in the demand, and over here, and then the rest of the uncertainties. For our imperfect information, this is the conditional probability matrix assessed by the SMEs, such that if in reality there's high demand, we'll recognize that 75% of the time, and 20% of the time we'll see it as mid and 5% low. In the low demand, it's non-symmetrical. So in the low demand, we'd never think it was high, but 30% of the time we think it's mid. And in the mid demand, it's 20% on both sides, 60% chance we'd see it as mid. So let's move over to the Excel model and get right into it. Here's our Excel model with the scenario presented, which optimizes the decision policy and the prices with perfect information. With perfect information, we don't develop the low indicator, and we have a high price for the high indicator and a little bit lower price for the mid indicator. This chart shows the NPV distribution relative to the reference case with a price of $49.77. We also could show here the comparison of the number of tickets sold, and in our reference case, we sold 2,600 tickets on average. But with this optimized perfect, we only sell 2,090. So first of all, let's change this to the imperfect information. And let's go double check our model to make sure we have the right conditional probability matrix. So we'll scroll down here. And here's the matrix we talked about, the 75-25 and the 0-30-70. And this shows the model is showing you the Bayesian version of that, even though this is not what's actually used in the model. It only utilizes these probabilities. So back to the dashboard here. So what we find out is that going from perfect to imperfect using the same prices and the same decision policy drops the NPV from $37,000 down to $28,900. That's a pretty big drop. There's still a value of information, but NPV is much lower. So the question is, can we do better than that? First of all, let's capture this result down here. So let's optimize these prices. Now, when we optimize the prices, let's optimize with the low indicator on. So we'll turn that on. That means we're going to develop if we saw the low indicator. And we'll go here to Data Solver. And we want to maximize, what do we want to maximize here? We want to maximize, oh, not the NPV 10. We want to maximize our expected value subject to, by changing F3 to H, so these prices here, subject to the prices being between 70 and 20. So we'll say that looks okay, and we'll say solve. Okay. So it came back with these prices. Let's capture that below. We can compare that to what we had before. So we were able to increase the MPV from 28.9 to 31.7. And the value of information increased substantially, and the number of tickets increased. And we did that by increasing, well, no, actually we reduced the price a little for the high, reduced by a couple of dollars the mid, and increased the value of the low. And why will we increase the low so much? Well, because there was, even though we thought it was low, there was a chance that it could be high. If, in fact, if we go over here to the model and look at the Bayesian probabilities, if we saw low demand here, there was a 31% chance of being mid and a 3% chance of being high. So if we just focused on the low demand and set the price too low, we'd lose some value. So this is a optimal pricing. And now let's look at the decision policy. What if I turned off the low demand? Let's see if that increases or decreases the MPV. It actually dropped the MPV to 29,170,155. Capture that down here as well. So what does this say? We always want to develop. We always want to develop, but we want to use these prices depending upon the outcome of the survey, which is a very different answer than what we got with the perfect information where we didn't develop the low. Let's turn the low back on. We'll see the curves change here, right? So we turn the low back on. Relative to our reference case, we've reduced the downside. We've also increased the upside. So how did that happen? Well, I have a higher price here than I did in my reference case. I've got $58 rather than $49. And I reduced the downside by actually having a lower price, $42 rather than $49. So I improved both the downside and the upside in this particular scenario. The number of tickets sold is actually higher on average. I'm now selling 27,000 tickets, where in the reference case I only sold 2,600. And my value of information is $3,000, so it's a pretty good investment. Let's do one other thing. Let's look at a cross plot of MPV versus the tickets sold. So the blue dots here represent the perfect information, and the orange dots represent the imperfect information. So this has the highest MPV and the highest tickets sold, so that's clearly the preferred alternative. And this is the P10 outcome. When I compare the MPV versus the P10 outcome, there's only 2 orange dots here, but there's actually 2 right here. They both have the same P10. The question becomes, can I stand this downside risk by developing the low indicator to get the higher MPV? Or would I prefer not to develop the low indicator, reduce my downside risk, but at the same time reduce the number of tickets? That's what I wanted to say about the value of imperfect information. So I hope you've enjoyed this 4-part video. And if you want a copy of the model, send me an email at brian@theputz.com. And you can explore the engine behind the SIP math and this particular model. Thank you for watching.